So to continue, how many atoms are there in 4 grams of copper? You're given the mass of copper, so we're here, and you get the atoms of copper. So you're here. You want to pass by the moles of the copper and then get the atoms of the copper, right? So to go from the mass to the moles, you need the atomic mass of copper. You get it from the periodic table. It's this one. Okay, so we're gonna start always with the given, you guys. So I'm starting with 40 grams of copper. So that is 40 grams of copper. I want to cancel the gram unit and I want to introduce the mole unit. So I know that I need to use the molecular weight. For every 1 mole of copper, this has an atomic weight or an atomic mass of 63.55 grams of copper. This way, I cancel the grams. The grams is here. So I canceled the grams of copper and I introduced the moles of copper. So now I am here and I use the molecular weight. Once you get the moles of the copper, we're going to go to the number of atoms in there. So we're going to use the Avogadro's number. Remember the relationship. For every 1 mole of copper, this is equivalent to 6.023 times 10 to the 23 atoms of copper. This is the relationship of Avogadro's number. So you want to introduce the atoms. So the Avogadro's number needs to be on the top because this is the atoms of copper, and that is equivalent to 1 mole of copper. Okay, do the calculations and get the answer in here. Please mind the sig figs. You need one significant figure, so that is going to be rounding times 10 to the 22 atoms of copper. Okay, so it's going to be 4 times 10 to the 22 atoms of copper. Similar over here. So I'm given now the moles. So I am here and I want the atoms. I don't need the mass. So I am in this section of this equation. I just need to use the Avogadro's number in order to get the atoms of nitrogen. Nitrogen is an element in the periodic table. And there, so that is going to be the atoms because nitrogen is made up of atoms. So 1 mole of nitrogen is equivalent to 6.023 times 10 to the 23 atoms of nitrogen, and you can easily get the answer. Okay. Another example, how many moles are there in 2.5 kilograms of zinc? Now I have the mass, and the mass is in kilograms. So I do have to change this into grams. I cannot keep it as kilograms because the molecular weight is in grams. So please pay attention to the units. We need the number of moles. We are given the mass. So this is the equation that we are going to start with. Let's start with the mass. It says here in grams, but I'm given it in kilograms. So I'm going to start with the kilograms and change that into grams. So I'm going to start with 2.5 kilogram of zinc, right? And I'm going to multiply this. I know that I'm going to change the grams into kilograms. So I want to cancel the kilograms. So I know that for every 1 kilogram, that is equivalent to 1,000 grams in there. So I can easily cancel the kilogram. So now I am in the mass of the grams, right? So I'm going to use the molecular weight of zinc. This is from the periodic table. And I'm going to get the moles. Here you go. So I want the moles to be in the numerator because this is what I want. And this is 1 mole corresponds to that much mass of, um, of zinc in there. Here you go. So this is the grams. This is the grams in there. And the answer is going to be 38.22 moles of zinc. Okay, this is just a conversion factor. So once you got the mass in grams, the grams is going to be the grams of zinc. So this is why the grams of the zinc goes out with the grams of the zinc as well. Find the mass in centigrams. So see here, I am just introducing these examples where you would need to change the mass into grams before you go ahead and you proceed. Okay, so find the mass in centigrams of 6.7 times 10 to the 10 atoms of magnesium. So whenever you get the mass, just to change it into, you're going to get the mass in grams. So at the end, go ahead and change it into centigrams. Well, I'm given the atoms, so I am here. I want to use the Avogadro's number, get the moles, use the molecular weight, and get the mass. Whatever I'm going to get will be in the grams. We're going to do a conversion and change that into centigrams. So let's start. Magnesium is an atom, okay? So it's an element in there. So this is why I'm working with atoms. So I'm going to start with 6.7 times 10 to the 10. This is my given 6.7 times 10 to the 10. This is atoms of magnesium, right? And I want to change this into moles, so I'm going to use the Avogadro's number. Changing it into moles, so the moles have to be in the numerator. This is 1 mole of magnesium for every 6.023 times 10 to the 23 atoms of magnesium. Okay, now I get the moles in there. So now I am here. I need to change this into the mass. So I'm going to use the molecular weight of magnesium. From the periodic table, this is the molecular weight for every 1 mole. This is the mass. I want to cancel the moles, so the mole has to be in the denominator. So for every 1 mole of magnesium, that corresponds to 24.31 grams of magnesium there. Whenever I do this, you guys, take a look. My answer is now going to be in grams of magnesium. So I can simply change that into centigram by knowing that 1 gram is 100 centigrams. So 1 gram is 100 centigrams. Every time, whatever you want to find has to be in the numerator. Okay. So the grams of magnesium, grams of whatever, because it's a conversion unit, so it's going to be grams of magnesium anyways. So my answer in this case is going to be 2.7 times 10 to the negative 10 centigrams. The mole concept can also be applied to individual atoms in the molecule. So we solved the problem similar to this one, okay, which was up here. So this is the similar concept, and this is the application of that. So if you are working with a molecule, you can simply divide this molecule into its individual ions or atoms, not ions, it's actually atoms. And you say that, okay, 1 mole of carbon dioxide molecule is made up of 1 mole of carbon atom plus 2 moles of oxygen atom. So you can simply relate the atom to the molecule in there. Please remember that every 1 mole is an Avogadro number. So 1 mole of that, this means that Avogadro's number of CO2 molecules is equal to the Avogadro's number of the carbon atom is equal to 2 times the Avogadro's number of the oxygen atoms in there. And that is equivalent to the molecular weight of the molecule that is equal to the individual masses of these atoms in there. And of course, if you have more than 1 atom, you're just going to multiply it by how much do you have. So oxygen here is 2, so it's 2 times 16, so this is why it is 32. You can also have this relationship in the cheat sheet. I wrote that for you. So let's have an example in here. So how many carbon dioxide molecules are needed to contain 50.00 grams of carbon? So carbon dioxide is a molecule, and carbon is an atom in this molecule. The first thing, which is so important, you got to figure out your given is for who? Your given is for what? Is it for the atom or for the molecule? Well, you are given the mass for the atom. So if you're given the mass for the atom, you have to calculate everything for the atom and then relate this to the molecule. Okay? So we're going to start with 50.00 grams of carbon atom. This is the mass of the atom. So I'm going to use the molecular weight of the atom. I cannot use the molecular weight for carbon dioxide. So I'm going to use the molecular weight for the carbon. Here you go. And let's start with a 50 18.00 grams of carbon multiplied by, I'm going to go from the mass of the atom to the moles of the atom. So I need the moles. So every 1 mole of carbon, that is equivalent to 12.01 grams. I'm sorry, this is the grams of carbon. That's true. This is the grams of carbon. So now I got the moles of the carbon. I want to change the moles into atoms and then relate the atoms into molecules there. Because once I change the moles into atoms, I can simply relate the atoms into the molecules, because the molecule is made up of atoms. So here you go. I'm going to change this into atoms. So for every 1 mole of carbon, see, I said carbon, not carbon dioxide, because I'm still in the same route that I need to calculate the moles of the atom, the number of atoms in the individual element in there. So 1 mole of carbon is equivalent to 6.023 times 10 to the 23 atoms of carbon. Okay, now I stop and I look at the carbon dioxide molecule in there. And I say, okay, carbon dioxide molecule has how many atoms of carbon? So I know that for every 1 molecule of carbon dioxide, right, I have 1 atom of carbon. So this is how I can calculate the number of molecules of carbon dioxide. So for every 1 molecule of carbon dioxide, I have 1 atom of carbon, 1 atom of carbon. If I wanted, so here you go. So how many carbon dioxide molecules in there? Yeah. The same question can be given also for oxygen. Okay. So this question can be given for oxygen. Instead of carbon, they can give me oxygen and I can relate it the same. But remember, for every 1 molecule of carbon dioxide, you have 2 atoms of oxygen. This is the difference. Okay. So remember, if that was oxygen here, then this here is going to be 2 atoms of oxygen. So please pay attention to that. As long as your units cancel out, so the atoms and the atoms cancel, the moles and the moles cancel, the grams and the grams cancel, and I am left with the moles of the carbon dioxide in there. Okay? Yeah, you can do the calculation for this one. Another example, what is the hydrogen, the number of hydrogen atoms? This one is similar to your homework, number 29. Just follow the same steps in there, and similar to number 29 and number 35. Okay, so just follow the same steps whenever you are working with these two examples. What is the number of hydrogen atom in a 18.016 grams of water? Water is what? Water is a molecule. This one is actually similar, kind of like similar to the one before it. So water is a molecule and they need the number of atoms. So since they gave me information about the mass of the water molecule, I need to continue and get simply the moles of the water molecule, get the number of molecules of the water, because I'm working with water, right? So I'm going to get the molecules of the water and then relate those to atoms. Okay, so let's start. Um, let's see. I'm given 18.016 grams of water, right? And I'm here. So I'm going to use the molecular weight and I'm going to get the moles. So I'm going to get the moles of the water. So 1 mole of water, get your molecular weight for this one. So calculate it. The molecular weight is 18.02. So that is 18.02 grams of water. Okay, guys. So once you get that, you got the moles of water. By simply canceling the units, you got the moles of the water. So now I want to go from the moles of the water to the molecules of the water. Why I need the molecules of the water? Because I know that water molecule is made up of hydrogen atoms, so I can relate to that. So I'm gonna go with the molecules of water, and again, water is a molecule here. Water is not an atom; it is a molecule. It's gonna be the same relationship as Avogadro's number here, which is the 1 mole of water, because I need the moles of water to cancel out. That is equal to 6.023 times 10 to the 23 molecules of water. Molecules of water. So what I did over here is that I introduced the molecules of the water. So now I am here. I want the number of hydrogen atoms. So I can cancel the molecules of water by simply putting a relationship that 1 molecule of water contains how much hydrogen atoms? It contains, see, water is H2O. So 1 molecule of water contains 2 hydrogen atoms and 1 oxygen atom. So that is going to be 2 hydrogen atoms. Okay, this is it. I got it. So molecules of water, you take those out, and then your answer is in the hydrogen atoms as it is asked. The answer is that much hydrogen atoms. That is similar to number 30 over here in your homework. What is the number of hydrogen atom? Let's see. We already did that. So number 30. Okay. How many moles of oxygen atoms are there in 1 mole of carbon dioxide? Okay, here you go. So if you take a look at carbon dioxide. 1 mole of carbon dioxide contains what? It contains actually individual atoms. It contains 1 mole of carbon atom and 2 moles of oxygen atom. This relationship is very important. So when I ask you how many moles of oxygen atoms are there in 1 mole of carbon dioxide, it's actually 2. So you have 2 moles of oxygen. You don't need any calculation for this one. Okay, so I'm given here 1 mole of carbon dioxide. Let's have another example. Okay, how many moles of hydrogen, or how many hydrogen atoms are there in 1 mole of ammonia? Okay, so I just want you to see the difference between this question and this question. In this question, I am asking about the moles of the oxygen atoms, and I can simply do it from this relationship in there. Okay, so I'm asking about the moles of the oxygen atoms. Here, I'm not asking about the moles of the hydrogen atoms, because if I'm asking about the moles of the hydrogen atoms, it will be 3. I am asking about the hydrogen atom. So please pay attention. Okay, so hydrogen atom in there. So this I need to do calculation for. I am given the moles, so this is the moles here, and I need the number of atoms here. So I need this portion of this equation. Okay, to go from moles to atoms, I'm going to use the Avogadro number in there, where it relates for every 1 mole. There is 6.023 times 10 to the 23, and this is for the NH3 there. So I'm starting with the given. This is the given. So 1.00 moles of ammonia NH3. Okay. I want to change this into, let's say this one is not an atom. I'm sorry. This one is a molecule. So I'm using the moles to molecules in there, because NH3 is a molecule. So let's relate this to a molecule. For every 6.023 times 10 to the 23 molecules of ammonia, that is equivalent to 1 mole of ammonia. You can cancel the moles out. You're left with the molecules. Now I can relate the molecules to atoms by knowing that for every 1 molecule of ammonia, this has 3 atoms of hydrogen. So 3 hydrogen atoms in there. So the molecules and the molecules will cancel, and I get the 3 hydrogen atoms. You can do the calculation for this one and get the answer. Another example, this is similar to number 24 in your homework. The formula for dinitrogen monoxide is N2O. If a sample of the oxide was found to contain that much oxygen, how many grams of nitrogen would it contain? You guys, this one you can solve it either by one equation or you can do steps. And the key for the homework, I did it in steps. So here I'm just going to solve it in one equation. So it's 2 ways to solve it, and you choose whatever method that you think is you understand better. So okay, so I am given actually the mass of the oxygen, and I want the mass of the nitrogen what it contains. So I know that N2O is simply a compound, right? It is a molecule in there. But the mass that I am given is for the atom. It is not for the molecule. So I'm given the mass of the oxygen atom. So if I'm given the mass of the oxygen atom, I'm going to get the moles of the oxygen atom. And then after this, I can relate the moles of the oxygen to the moles of the nitrogen. And then I can go ahead and get the mass of the nitrogen by using the molecular weight. You guys, the molecular weight for oxygen, that is 16.00 grams per mole. And you definitely need the molecular weight of nitrogen as well, which is 14 grams per mole. Okay, I'm getting those from the periodic table. So let's start over here. I am starting with the mass, which is the mass of the oxygen, 0.0800 grams of oxygen in there. So what I want to do is I want to go from the mass of the oxygen to the moles of the oxygen, right? So to do this, I know that 1 mole, I'm going to use the molecular weight of the oxygen, okay? So I know that 1 mole of oxygen, that corresponds to 16 grams of oxygen. So I'm going to take the grams of the oxygen and the grams of oxygen, cancel those out. And now I'm left with the moles of the oxygen, right? Okay. So since I'm left with the moles of the oxygen, I want the grams of the nitrogen, right? This is what I want, but I cannot go to the grams of the nitrogen without getting the moles of the nitrogen, because the route to get the grams, you need to pass by the moles. See, mass of the oxygen, you get the moles of the oxygen. You can relate the moles of the oxygen to the moles of the nitrogen, and then from the moles of the nitrogen you can get the gram of the nitrogen. Okay, so let's go ahead and do this relationship over there. Moles of oxygen to the moles of the nitrogen. N2O, it's given the molecular formula in here, which is N2O. I can see that in the molecule, for every 1 mole of oxygen, I have 2 moles of nitrogen, right? So that is going to be for every 1 mole of oxygen. I need this in the denominator so that I can cancel the mole of the oxygen, introduce the moles of the nitrogen in there. Once I get the moles of the nitrogen, then I can go to the grams. Moles, grams, I'm going to use definitely the molecular weight of nitrogen. So I know now for every 1 mole of nitrogen, that is equivalent to 14 grams of nitrogen in there. So if you go ahead and take out the units, then I'm going to be left with the grams of nitrogen, not 14, I'm sorry. I'm going to be left with the unit, which is the grams of the nitrogen, which they are asking me about in here. So the answer is going to be 0.14 grams of nitrogen. Okay. This is another example. It's similar to the one in the homework. um, which of the following has the largest mass? You're given the number of moles of each one of these molecules, and you want the mass. So you're given this, you want to get the mass. So just go ahead and do a relationship as we did. I'm gonna do. Actually, I need to do it for both. So since water and ammonia, these are molecules in there, we're gonna use the molecular weight of the molecule. Go ahead and calculate the molecular weight of the molecule, and then we're gonna start with the moles. So that's gonna be 3.0 moles of water. And I want to change this into grams of water. So I know that for every 1 mole of water, use the molecular weight. This is water, it's not 18. The 1 mole of water, that corresponds to 18 grams of water. Okay, so that is equivalent to 54 grams of water. Cancel these. We're going to do the same thing for ammonia. We're starting with 2.5 moles of ammonia. And we're going to change this into grams. So for every 17 grams of ammonia, that is equivalent to 1 mole of ammonia. So take the mole out, and that is 42.5 grams of ammonia in there.